I wanted to talk today about what are we doing with event-based cameras in the real world. And really it's an excuse, it's more of a highlights reel to show you some cool videos that we've made with these event-based cameras, because I'm really proud of some of the ones that we have. So in terms of applications of event-based vision, one that we've been working on and that some of you may be familiar with is using them for satellite tracking to determine where satellites are. This is a setup from 2017, so about 6 years ago, and I hope you saw that thing shoot through in the top in the top left there. So we had an event-based camera, a fairly old one, on the back of a telescope. We were just tuning it to see if we could get the biases right and whether we could see anything, and we were about to point it at the star, and something shot through, and we went, hey, what's that? And that was a satellite, and that was our first glance of a satellite, and that we could catch those with them. Yeah.
In plain day, right?
This was during the day, yeah.
Well, twilight, right?
Yeah. And when we then started looking at actually tracking a satellite, so here this is a rocket body that we're tracking. On the left is the footage from the event-based camera. On the right is like a time cube of it. And then because we're tracking a rocket body, the stars that we go past will shoot through, and they'll all shoot through in the same direction. So this was at the very beginning that we were looking at that. And when we started this work, I didn't realize why you would want to track satellites all the time. I thought satellites are like planets and stars. Once you know where they are in orbit, you can predict 1,000 years ahead, and you know that they're going to be there. That's actually not true at all, particularly the lower Earth orbit ones. They're much smaller than planets and stars, therefore they're much easier to move about. So they're subject to solar winds. The low Earth orbit ones, they get some atmosphere from the Earth, still some effects there. And their orbits, they're only good for about 24 hours, basically. And because you're looking through a telescope, you're basically looking through a straw at the sky. You see a very tiny part of the sky, and if you're pointing the telescope in the wrong direction because your orbit prediction is wrong, then you won't see it, and then good luck finding where it is again. So that's why every day, everything that's going around the Earth needs to be observed at least twice, basically. And so there's a business to be made there. And currently, optically, it's done like this. So here you take a video or basically a picture with an astronomical camera, and then 5 seconds later you take another picture with a long exposure time. That's why the stars are moving. And 5 seconds later you take another picture.
Sidereal motion, right?
Yeah. So in this case we're actually tracking the satellite. So can you spot it?
No.
So let me see if I can do this here. If I grab it, can you see it now? Right, that's the trick, right? One of the things, for us at least, for the eye, you have to move things. Well, and then you see the steady point. Well, it actually moves a little bit. You can see it, but
right there, right?
Yeah, right in the center here, right?
Oh, I see. I thought it was that bright spot. Yeah.
The entire game up there is not to have your satellite shine, basically, right?
Yeah.
Yeah.
So that's so we developed that into what we call our Astrocyte. Nice pun on the name. Which is basically a converted shipping container, sliding roof, garage door opener for the roof, a lift in there to lift the telescope out, and then the telescope comes out and we do our observations remotely and automatically, as you will see in a moment. So this is one that we deployed in Australia, in the outback. It's fairly flat around there. It's a nice dark area too, so you don't get much light pollution around there. And the nice thing about these is you can deploy them anywhere. There's a whole industry made around transporting shipping containers around the world. So you can take it, drop it, set it up in a day, start doing observations with it. And that's where the event-based camera gives us an advantage, is we don't need such a stable base as for those photos that you saw. For those, you need astronomical camera in an astronomical observatory that's on a big concrete slab, usually on top of a hill somewhere. And everybody knows too where those observatories are. Here, any shipping container around the country could actually be an observatory, which is also an advantage for them. So we've developed the software. This is sped up, but to operate it remotely, to do these observations, we task it remotely. At the moment, we're running it constantly. That one in the desert is doing about 500 observations every night. We're recording that data. Obviously, when it's cloudy or raining, we can't use it. But luckily, the weather in the desert is quite good, so we can.
Those green streaks there?
Down the bottom,
Yeah.
they're a subset of where the satellites are projected onto the sky from the data.
Andre,
Yes.
I keep asking Greg, do you see weird stuff up there?
Not so much from here, no. But we do see some weird stuff. You'll see some later when you're up there.
Back to my question. So.
Yeah, no. From here, I mean, unless you call like two satellites meeting up and parting again, things like that, which are exercises that have, particularly in the geostationary belt. So
They do refueling, right?
yeah, things like that, or like spying on each other and stuff like that. So low Earth orbit, for those that don't know, that's about 400 kilometers above ground, whereas the geostationary ones, the ones there where your TV stations and so on all are, that's about 36 to 40,000 kilometers above ground. So that's a lot further, right? 100 times further. So we've also written the processing of the event. So we you notice both objects are moving, but we use the stars as our point of reference, and then we localize the object that is our target with respect to the stars. So the stars are our stationary reference frame, and then we can tell exactly where these objects are. We extract this automatically in the recordings that we do now, so we don't need human processing in the loop. And we have two of those, and we're about to build a third, and we're about to spin this out into a company that will start delivering this as a commercial service. We're hoping that this company will be up and running sort of August this year. So that's one application area. Now let's take this to space itself. Go the other way. Well, how do you get to space? With a rocket. Not this one, it's a sounding rocket. Wouldn't get you very, very far, but still. This is a NASA launch, the first one, or at least the first one in a very, very long time in Australia, from the north of Australia. And on the right, you can see with the standard camera, it is overexposed for most of the part that you're interested in once that rocket starts. So the rocket is almost gone out of the field of view before this camera recovers from that. Whereas on the left, you can even see, and I just missed it, so I'm going to go back. You can see the stabilizing rockets fire as the second thing. So when it reaches the top up here, you'll see that happen in the slow motion. And look at the amount of detail you get just from the event-based camera. In this launch, from the exhaust that you get.
Can you point to where the steering?
Yeah, so it's about here.
Yeah.
See, the side jets, they make them spin, and that stabilizes them in flight. So now you can't. Hang on. Go to the next one. So you can't set that up right before the launch, like the last few hours before the launch. You're not allowed anywhere near the rocket. So you set it up hours ahead, and you can monitor your event rate and speed up and slow down if you want. Like we're slowing down here because we saw a nice shooting star that you'll see in a moment in this hour-long footage. There you go. Wasn't what we were looking for, obviously, and then you speed it up again because there's nothing much interesting is happening, and you look at the event rate, you see clouds come by, they change the event rate a bit because of course they generate some events for you.
You have a megapixel, right?
Yeah, this is the Prophecy Gen 4 sensor, yeah. So it's,
Clouds going by or something?
those are clouds going by, and you can see here the event rate that the rocket is going to launch in a moment, so we slow it down, and you can see that actually the event rate looks like it's saturating right at the start of the launch. Again, you saw the the spinning rockets at the end, and here at the end you'll also see the second stage firing after, but by then we're covered in smoke, and you see some bits shooting off. I hope they were supposed to shoot off those bits. I'm not really sure. So here it extinguishes, and then there's another one coming. Yeah, there. So a second firing, and then we speed it up again. Okay, so we look at rocket launches with this. We think that's quite a nice use of these event-based cameras to extract information from the data. But I was saying, let's take this to space. So in December 2018, we launched this Falcon Neura payload to space. It's on the International Space Station on the Columbus module. Those are two Davis 240 cameras, so quite old ones that we put up there. We wanted to start with cameras that we understood really well. On the left, you see an image taken from a high-definition camera up there that is mounted near where our equipment is mounted. On the right is a rendering that we make from the data we get from the event-based camera that's looking down. So I said we have two up there. One's looking down, one's looking forward at the horizon. So this is the downward-looking camera. And as the space station moves, of course, you're scanning the Earth like you're peeling an apple, basically, and you can render an image around that. So here's an example of doing that. So this is above Egypt, so Alexandria down here, down the bottom, Port Said here, Suez Canals through here. And as we go, we can build up that image and overlay it on the Google map. I take it away now, the features that we see. And so this is taken at night, so we mainly see the lights of the cities here, but we can also see the other one, the previous one. This was taken during the day. And you can see some cloud coverage in there as well. So if you want to see more about the downward looking camera and the things we do, Sami, who's here in the audience, he has a poster about this today that you can look at. So this is the raw data from the RAM recording, which is looking forward at the horizon. And you go like, that's not all that interesting, is it? It's not a lot to see, you think, right? And I must apologize, by the way, I forgot to do that at the start, for the people on Zoom, because these type of event-based images, the video encoders for Zoom really don't work very well for these type of images. So you get really poor data. But in this case, there isn't really a lot to see, at least at first instance. We thought as well, right? You saw some streaks down the bottom maybe and so on. But if we do what Riyadh was talking about, a bit of time surfacing, and the other trick, the one that I did with the astro photography, where you jiggle it back and forth. We actually do call that jiggle. So we time surface and jiggle, and this is what you see. So you see features from the Earth down below. The horizon is here. You see the stars go up, and there's a satellite there that you see shooting through. So we can label those and see if you see it. So that's the stars all going up, giving us a nice reference frame for this data.
There's even something else there, right?
Yeah.
Many things.
And we're still missing one. Look, there's one up here that we haven't right up here at the beginning of the recording. There's another one that shoots out a frame. No idea why so many, because most of the time we don't see this many, but this is a really nice recording for it. The other thing you recognize from the Davis 240 is this bright line, dark line, bright line, dark line, bright line, dark line. That's still there, and you can process all this out, and a lot of fixed pattern noise that you can see in this, right? I haven't processed here. Again, of course, you can subtract fixed pattern noise reasonably well.
So stars.
Yeah.
Huge.
Yeah.
Crazy.
So it went up there as this nominal scientific mission, to put it up there, is to look at lightning, and particularly what are called sprites. And sprites are lightning that goes from the cloud to the upper atmosphere rather than down to ground or between clouds. We can see lightning, as you can see here in this footage. Again, processed the same way. We're jiggling it back and forth. The time surface is a bit shorter here, so it's a little harder to see the stars, but you can still see the stars move up and down in this image. But there, the resolution really is not that great on these cameras, and the event lasts very briefly, so it's a real issue for us. For looking down, scanning the ground, yes, the camera has low resolution, but because you detect the edges with very high temporal resolution in the direction that you're moving, you can actually build up a picture with quite high resolution. Across you can't, because there's nothing you can do. But with lightning we can't do the same trick. So now let's do this on the ground here with a better camera. So we'd a more modern camera, let's be nice about it. And we record a lightning strike, and you can also do this with a high rate frame-based camera, which will set you back about $100,000 US, and weighs about 8 kilograms, and can record for like 5 seconds or so, and then its buffer is full.
In power of thousands.
Oh yeah, and it costs a lot of power. So now we can slow this down 400 times. You can see the raindrops falling nicely. You can watch the lightning form. You can track the leaders of the lightning and so on. And really study the lightning. Now, if you want to get really bored by lightning, if you didn't think it was possible, but this is slowed down 20,000 times, basically. So it's like every microsecond is an update, basically, to this frame. You can see it's kind of matrixy, right? The rain has stopped falling, but everything else is like this lightning is moving a little bit, and so you can really track the points of the lightning with these cameras quite well. So with these newer versions, we can see lightning much better. So we're taking 2 of those up to the International Space Station next year. That's being built at the moment, so that's going to be Falcon Odin. And next week is the engineering design review for that one in Colorado. And the difference, well, it's a much bigger package. It will have steerable mirrors in it, so we can adjust where it's looking. That's a big change and a big thing for space. Like when you're on a satellite, having moving pieces really becomes an issue, because when you move one of these things, the International Space Station moves. It's a little bit, but it's like there's nothing holding it in place if you don't do it right. So
where's the camera here, and what are the mirrors?
So the cameras are down here. The mirrors are steering the field of view. And then there's a zoomable lens on there for the ground-looking camera as well. So we can, change the zoom. So the difference is that crosswise is at the moment Falcon Neuro on the ground has a resolution of about 250 meters. As I said, in the direction that we're scanning, it's better than that, but in that direction it's 250 meters. And with this setup, we'll be down to 6 meters resolution that we should get. And so that's going up next year. And this is a model of the payload, basically, so you get an idea of the size of what is going on there. So, talking about steerable and zoomable optics, we got a chance to fly this camera too on a Cessna with a very nice gimbal on it, with some nice optics. And this is just, again, showing off a video. We don't really know what to do with this yet, but clearly you can get some nice data of your cars here.
The Cessna is flying, but it's being stabilized.
It's stabilized by this gimbal. Yeah, it's incredible, huh?
Yeah.
Look at this zoom.
You built a FLIR, basically, better FLIR.
Yeah, it's.
Check the traffic camera. Check the speed.
Yeah, traffic camera. Probably, like you check the tail length or something like that, and it tells you about the speed because of the time surface decay. Yeah, if you set it right, you can do that just right. So, and let's see if you can guess what this is.
A bridge? No. A building? Reflection?
An opera house.
Somebody will get it. Driving range. Does anybody play golf?
Golfing range. Oh, multi-level.
Multi-level driving range, yeah.
I can show you beautiful people shooting a gun.
So the things that you see shooting through, well, not the one that went really fast, they don't hit them that hard, but there you can see the golf balls shooting out. This Top Golf in Colorado.
No? There's one where you see bullets passing by, no?
Yeah, we don't have that here. I didn't put the bullet stuff in here. So, and really those were, well, I have one last video that I'll just let play in the background while I take questions for in the interest of time. Again, it's like a guessing game, this one, to see if you can figure out what you're looking at here. And I can take questions in the meantime if you want.